Hello lovely grade 12s. This is a follow-up on the video on the number e. So pretty much in the previous video we discussed the number e and we said e is the number 2,718. And we followed up on that saying if I go and I have the function y is equal to e to the power of x, then the inverse of that function is going to be the ln function. Now in the previous video we also said ln is a logarithm, but it's specifically a logarithm with a base number of e. So we are now going to go and after we've discussed all of those log laws, in this case ln laws in the previous video, we're going to do some examples on how to solve exponential equations with e and how to solve logarithmic equations using ln. So this is an example from the textbook, example 1, page 6. And as you can see it says, solve for x if 6 to the power of x plus 2 is equal to 2 times 3 to the power of 2x, and they ask specifically that you should give your answers in terms of ln 2 and ln 3. Now, this is an exponential equation, but it's not a stock standard exponential equation because normally in an exponential equation, you have base exponent equal to a number. And clearly on that right-hand side, you don't have a number. You've got another base, you've got another exponent. So we can't just convert that into logarithmic form because it doesn't actually allow us to simply convert to logarithmic form. But because they ask for the ln in my answers, I'm going to go and simply just start by saying put ln on the left-hand side and put ln on the right-hand side. And logically speaking, I'm perfectly allowed to do that simply because of the fact that I can do whatever I want in an equation as long as I do it on both sides. Now, what that ln allows me is the moment I put the ln on the left-hand side and the right-hand side, I am now allowed to use all of those logarithmic laws that I discussed with you in the previous video. So the first logarithmic law I can use over there is I can take x plus 2, my exponent, and I can move it to the front of the logarithm or the ln multiplying by it. So I can go x plus 2 times the ln of 6 is equal to, and now over here I can actually do more than just what I did over there. I've got a number 2 multiplied by 3 to the power of 2x. Now the whole thing is if I have two numbers multiplied by each other, that's going to be that law, the multiplication law, in reverse. So please remember we said if I have two logarithms added together, it becomes one logarithm that is being multiplied. So if I have one logarithm being multiplied, I can split it up into two logarithms being added. But I'm also going to go and say, when I split this into my two logarithms, there, because of that to the power of 2x, I'm going to do the same that I did over there. So I'm going to do two things using law 1 and using law 3. And that's going to be the ln of 2 plus 2x times the ln of 3. And then you can start seeing where this ln 2 and this ln 3 starts coming in. Right, so over there, we can obviously now go and multiply x by the ln of 6, and we can multiply 2 by the ln of 6. But again, we don't want it to be the ln of 6. We want it to be the ln of 2 and the ln of 3. So I can easily break up that ln of 6 saying the ln of 6 is equal to 2 times 3. But because it's 2 times 3, I can then go and I can use that lovely log law to split it up into the ln of 2 plus the ln of 3. So please note, two things happen here. I said 6 is equal to 2 times 3, and because it's the ln of 2 times 3, I can then say it's the ln of 2 plus the ln of 3. And over there, I'm just going to write it down as is for now. Right. Now, over here, I've got a binomial times a binomial, which means I'm literally going to have to go and multiply first. I'm going to have to multiply outers, I'm going to have to multiply inners, and I'm going to have to multiply last. So I'm going to do that next. X times ln of 2 plus x times ln of 3 plus 2 times ln of 2 plus 2 times ln of 3. And then over on that side, I'm still keeping the ln 2 plus 2x ln of 3. Right. Now finally, I have terms that I can now go and keep all the x's on the left-hand side because that's what I'm trying to do. I'm trying to solve for x, and everything that doesn't have an x goes to the other side. So simply doing that quickly. And then just check this. I've got the x ln 2, x ln 3, and then over there I've got the minus 2x ln 3. And then I've got my ln 2 minus 2 ln 2 minus 2 ln 3. Now, over there, I'm going to take x out as a common factor because these are not like terms. So obviously I can't add and subtract them. So I'm going to have to take x out as a common factor. And over there, I've got some like terms. So I can actually simplify because I've got ln of 2 minus 2 ln of 2. And those are like terms. It's one of those ln 2's minus 2 of those ln 2's gives me minus ln of 2. And then finally, in this bracket, I also have some like terms. I've got ln of 3 minus 2 ln of 3. So that will obviously simplify to one of these ln 3's minus 2 of these ln 3's will also give me minus ln 3. But I'm going to simplify and I'm going to divide by that bracket to get x on its own. So solving for x is equal to minus ln 2 minus 2 ln 3 divided by ln of 2, and then that simplified version, which is minus ln of 3. And that is my final answer. You might see it slightly different in the textbook, but in the textbook they might have gone and said, okay, these minuses can go to the bottom. So you can take it out as a common factor. So possibly it could have looked like this, saying it's minus ln of 2 plus 2 ln of 3 over ln 2 minus ln 3, and then they could have gone and distributed that negative, saying let's move it to the bottom and distribute. So this would have become a positive ln 3, and that would have been a negative ln 2. But you can stay with this version because you have answered the question. You've given the answer in terms of ln 2 and ln 3, so that's the answer. Now this, yes, I agree, is quite complicated. It's just a little nudge to start practicing these log laws, because unfortunately in core mathematics, even though we teach you these log laws, I mean, you've never seen anything like this. You've never seen us expand it like this. You've never seen us put it back like this. So logically speaking, this is just to get you guys practicing. Right, so the other example in the textbook is way more straightforward, and this is more the type of question you can get in an exam. So it says, solve for x if e to the power of 2x minus 4 times e to the power of x minus 5 is 0. Now, just because it's got that number e, please people, do not get stuck on the number e. What you should see over here is you should see an exponential equation. And more than that, you should see an exponential equation that's got to the power of 2x to the power of x, and then logically speaking, this is like having e to the power of 0. So this is exactly like the exponential equations we did with you in grade 11. It's a quadratic exponential equation, which can be factorized into a binomial times a binomial. So you're more than allowed to use k substitution if you want to. So if you want to try it with k substitution, you can set k equal to e to the power of x. I'm not going to use k substitution, because you are AP Maths people, so you should be able to factorize this, no problem. So factorization, we're going to say it's a binomial times a binomial, and we're going to say e to the power of x times e to the power of x is e to the power of 2x, because if I multiply these powers, I add the exponents, which gives me that e to the power of 2x. Then I need to get that 5, which is 5 times 1, and then I need to have minus 5 times positive 1 to get the negative 5, but also to get that minus 5 times e to the power of x plus 1 times e to the power of x gives you the minus 4 times e to the power of x. Then finally, all I need to do to finish this up is say e to the power of x is 5. Now that is a valid answer because e is 2,718, so it's a positive base. So if I have a positive base to the power of x, then it could very well be equal to a positive number. But when I write this one down, so if I go or e to the power of x is equal to negative 1, you should immediately realize that is not possible. It's impossible to have a positive base be equal to a negative number because there's no exponent that will change a positive number into a negative number. So if you did accidentally continue with that, you would have actually spotted there's going to be a mistake over there, but you should immediately go and say this is not a valid solution. Now to finish this one up, I need to now go and solve for x. And this is the part where x is in my input position. So I need to now make x go into my output position. But the only way I can change x from an input to an output is if I use the inverse function. And please remember the inverse here is ln, because ln stands for log base e. So I've got log base e, which means the base has already been used, and that number 5 is then going to go over there. So that's your answer. Now, depending on how they set up the question, if they say you've got to solve it correct to 2 decimal places, then you put that into your calculator. But most times they actually say solve without the use of a calculator, leaving your answer in terms of ln. So I'm going to leave this answer in terms of ln, but if they do say correct to 2 decimal places, you just put ln of 5 into your calculator. So this is very, very, very common. There's been quite a few questions like this in the past papers. So you can actually go, and if you look through your past papers, you'll see lots of these. Right. The next example, which is the last example from the textbook, says solve for x if log of e to the power of x plus log of xe, sorry, not power, that's the base, log base ex plus log base xe is equal to 2, 5. Now, the first thing you should see is that they've written this as log e, which interestingly enough, they should have written it as ln of x, because log base e is actually ln. Now, the reason they did that was specifically so you could see in this logarithm, e is the base, x is the number. But in this logarithm, they've been swapped around. Now, this is not part of one of your log laws per se, and it definitely doesn't appear on your formula sheet. But you will recall I showed you some deductions from the log laws yesterday. In the previous video. I recorded it yesterday, so I'm thinking of yesterday, you're just thinking about the previous video. This is going to happen quite a lot, so excuse the confusion. So if you look at this, you'll see I've got that e, and I've got the x, and I've got the x and the e. And if you recall, one of the deductions, it was the second deduction that I showed you in the previous video, said I can swap the base and the number around as long as I write this as its reciprocal. So I can go and say this is log base ex plus 1 over log base ex. And that was shown in those deductions, and I also explained to you why this is a valid deduction of specifically the log law 4, which is the change of base law. Now that 2, 5, I'm going to rewrite that, and I'm going to say that's 5 over 2. And then what you should notice is this is an equation with fractions. And how do we solve equations with fractions? We multiply by the LCM of the denominator. So I'm going to multiply each term by ln of x. And the reason I multiply by ln of x is because that's what these are. Log with a base e is ln, so I can shorten this to the ln of x plus 1 over the ln of x is equal to 5 over 2. Now that 2 is also part of the denominator, so technically speaking, I shouldn't just be multiplying by ln x, I should also be multiplying by the 2. So I multiply the first term by 2 ln x, and I end up with 2 ln of x squared. Please note, it's not just the x that's being squared, it's the entire ln that is being squared. Plus 1 over ln of x, and if I multiply that, sorry about that, if I multiply 1 over ln of x by this, I'm going to end up just with 2. Apologies about the little bit of a mess there. And then if I multiply 5 over 2 by 2 ln x, 2 will divide into 2, and I'm going to be left with 5 ln of x. So that's 5 ln of x. There we go. Now, if you look at this, again, I've got a square over there. And I've got 1, 2, 3 terms. So this is effectively, again, it's a trinomial. So I'm going to just put it in standard form for you guys. So it's 2 ln x squared minus 5 ln x plus 2. And that's going to be equal to 0. And now I'm going to factorize. And this is going to be 2 ln x times ln of x. And then that one's going to be 2 times 1. And I'm going to put a minus minus, so that if I multiply the two negatives, I get the positive. And over here, I've got minus 4 ln x minus ln x, which gives me the 5, minus 5 ln x. Then to finish up, ln of x is equal to 1/2. Or ln of x is equal to 2. Which then means, and careful with this one, because everybody always forgets, right there's a base e. So if I now want to go and I want to solve for x, I need to recognize that it's e to the power of 1/2 is equal to x, or x is currently the input. I want to make x the output. But the only way I can make x the output is if I change my ln function in this case into the inverse, which is e to the power of 1/2. Or, same thing over here, x is equal to e to the power of 2. And then depending on whether they say solve this to 2 decimal places or whether they say leave your answer in terms of E, you can then just leave your answer like this and you can say these are then my 2 answers for that particular equation. So I'll put up another video because this one's getting a little bit long. So these are the examples in the textbook. The last video that I'm going to put up for this week's AP Maths lesson is going to be specifically examples from past papers. So I will do that for you guys. The last video will look at past paper examples. Thank you for listening.